The next talk will be by Donggun Lee, and it will be about representations on the cohomology of the moduli space of pointed rational curves, permutation representations, and log concavity.
Okay, thank you for the introduction. And I'm very grateful to the organizers for this wonderful workshop and this chance for me to give a talk in front of this many experts in this area. Okay, I'm going to talk about the representations on the cohomology of some moduli space of curves. And I'll focus on two interesting features, two phenomena which we observe, namely being permutation representations and log concavity. So these are based on two joint works with Jin-Won Choi and Young-Won Kim. And one of the two papers was uploaded yesterday to arXiv. So you can see it on arXiv. Okay. Maybe I'll just. Sorry. Yeah. Okay. I'll start with the definition of M0n. This is a space of configurations of endpoints on P1, which are distinct and ordered. And we are considered all the configurations up to PGL2. So for example, when n is equal to 3, we can always move 3 distinct points on P1 to 0 and 1 and infinity by PGL2 action. So this is a point. And when n is equal to 4, then we have one extra point. And it should avoid 0 and 1 and infinity. So M04 is a P1 minus 3 points, which is just a C, a fine line, minus 2 points, 0 and 1. So it is always n minus 3 dimensional. And in general, if we consider M0n plus 1, then if we fix the first point at 0 and the second point at 1 and the last point at the infinity, then we can embed this space as an open subset inside an n minus 2 vector space, affine space. And then we can compactify this in the projective space. And you can easily see that this is the open complement of the hyperplane arrangement. And more precisely, this is the complement of the braid hyperplane arrangement or root arrangement of type A. So the projective space is the one of the easiest compactification of our M0n plus 1. And one of the most important compactifications of M0n was given by Knudsen. And in the notation, we put bar over M0n. And it parameterizes curves with the endpoints. But here we allow nodal singularities, which means in the nose here, we allow, it locally looks like x, y equals 0 in a two-dimensional affine space. And every point should be distinct and away from the nose. And also the number of special points, the markings or nodes are special point. The number of special points on each component should be at least 3. So this is how he compactified the space. So for example, when n is equal to 3, then it is already compact, so it's a point. And when n is equal to 4, we need to fill in the 3 points. And each of 3 points, for example, at the 0, we sprout a new component, new P1, when 2 points collide. So here we have two more points. So yeah, here we can separate 2 points to be distinct. So defined M0n bar is a compact space, compact manifold, with a natural Sn action on the space, which permutes the markings. Here our points are all ordered. So if you change the order, then the order of the markings, then we get a different class of curve. So there's a natural action. And actually this map is an isomorphism, so which means the permutation of markings is the whole automorphisms of M0n when n is at least 5. So here's the problem. We want to compute the Sn representations induced on the cohomology of this M0 in this moduli space. So this is harder. This is hard. This is harder than when considering some restriction of the action to the Sn-1, which fixes the last marking. So we will consider that first. So there are well-known facts about this compactification. So one is this is a wonderful model of the hyperplane arrangement of the type A, as we said before. And equivalently is a sequence of blowups of the projective space. So blowup means you replace some subset as some projective bundle over that. So we replace the endpoint with by some Pn-3, then we replace the lines by another thing and plane, etc. So then we arrive at this space. And I want to point out that in the previous observation, here there's a natural action of Sn which permutes the coordinates and which preserve the diagonal. And here we can consider the Sn action which permutes the first n markings and keeps the last marking fixed. And this compactification is an Sn equivariant model. And these blowups are also Sn equivariant. And there's one more fact we used in our paper. There's a more useful description of all the intermediate spaces appearing in this factorization, and also contribute in the blowups. Yeah. So there's a nice interpretation, so we can use that. So combining these two, in principle, we can compute the Sn representation on the cohomology of this space, not n plus 1. So we achieved that in our paper. But before moving on to the next page, I want to mention that, this cohomology is the charring of the braid matroid. So maybe this is already familiar with you. But yeah, we're not going to use this fact, but I just wanted to point out. So basically, we are considering the Sn action on the vertices, and that induces a representation on the charring. So we want to compute that charring first. And this is the result. This Sn representation is the permutation representation spanned by this set. So meaning that this is as a vector space spanned by this set. And the representation structure comes from the Sn action on this set. So here the Sn action is just a permutation of n inputs. Okay. The more precise definition of the weighted rooted tree is a pair of a rooted tree and a weight function. So the way we define this weighted rooted tree was coming from how the basis looks like. So we just copy. I mean, yeah, this comes from how it looks like. Yeah, that's how we define these objects, combinatorial objects. Okay, so this is a rooted tree with a root and one distinguished leg, which we call output, and the others are all called inputs. So we allow n inputs here, and we put some weight function on the set of vertices, and with some conditions here. So I want to point out, like at the root, this is the root. Root is allowed to have a 0 weight, but the others is not allowed to have a 0 weight. Okay, so in this way, we get a combinatorial formula for this representation. So here I'm considering the Sn action on the space of n plus 1 points. Okay. Then our goal was to compute Sn representation on this cohomology. but we just computed this space, this representation. So we want to relate these two. I mean, it would be good to relate these two. And we achieve that. So to state the formula, I'll just considering, yeah, this is what was called as an equivalent Hilbert series in the previous talk. So this is just a kind of Poincare polynomial, but with a representation theoretic way. Yeah. So we have a formula, combinatorial formula for Q, which parameterizes this representation, and P is our goal of this representation. And they are related by this formula. This is what we settled on. So if we can compute Q, then we can compute P. This is what formula says. And how we get this formula comes from basically geometry of the map, this map here. So this map is this is a space of curve with n plus 1 points, and this is a space with curve with n points. So we just forget the last marking. So it should be the equivalent under the permutation of the first n markings, right? So this is already, there's an SN action, there's an SN action. The map is SN equivalent. But we didn't know really about the good factorization of this map. And we found one, and applying some geometric theories to this factorization, then we get this formula. Okay. So as corollary, we get a formula for Pn as a sum over trees, because Q is already written down as a sum over trees. So for example, here, if you take, so already, yeah. And yeah, furthermore, if you take a coefficient of t to the k here, in the left-hand side, then we get this representation. And then using that formula, we prove that this is a permutation representation. And also for, this is for all n and k. And also for a single cohomology, but in this case, we only computed for up to degree 6. So here, permutation representation means it admits an invariant basis. So there's a basis of the vector space, and there's an SN action, and the representation comes from that SN action. That's what it means. So it's it's a kind of a positivity property of the representation. Okay, so this partially answers the question by Ramadas and Silversmith about whether a single piece of this cohomology is a permutation representation or not. It was previously known for the degree up to 4 by Farkas and Gibney and Ramadas and Silversmith. They gave explicit basis, permutation basis. And also, if you sum up all the degrees, then we know that it is a permutation representation by the result of the Kostrup and Tebelev. Yeah, they use a different theory. They use the derived category, and so the point is that their method does not apply to the single piece. So our result to refine all of these too. Yeah, so this is the result of our first paper, and then I want to move on to the second part. Low concavity. So this is about some positivity of our representation, and this is about low concavity. So our approach reveals some low concavity phenomena also. At first, we will first restrict to the invariant parts, which means we'll see the multiplicities of the trivial representation, and this is my notation of the P or the Q. The trivial part of the large P and trivial part of the large Q. And by the previous proposition, this is just a number of weighted rooted trees. So we have already combinatorial formula for this. This is just a count number of trees. And I want to roughly show how we count the numbers of trees. So okay, this is the way I count. We first fix a rooted tree without inputs, and also fix the weight function on that tree, then we count the number of ways we can attach the inputs at each vertices so that the defining conditions are satisfied. So an easy observation is that if you increase n, then the dominating part comes from the trees, this part, and also these parts, coming from the trees with the maximum number of vertices. So asymptotics are very similar to the number of ordered partition of n. So if you want to compute the asymptotic formula, so you only need to see the trees with the maximum number of vertices. So that's an easy observation. So using that, we established the formula for the asymptotic formulas for the trivial parts. So the numerator here is the k-list formula for the labeled trees with the k plus 1 vertices. And here k factorial is just a sk factorial. We can permute the vertices. And we obtain the formula for p using the formula we established, which relates p and q. So that's how we established this one. So using this, you can easily check that the low concavity of these two sequences for given k holds when n is sufficiently large. So in the geometric terms, we can say that the Poincare polynomials of these two quotients satisfy a low concavity asymptotic sense, in an asymptotic sense. The analog for M0n, which is not quotient, before taking quotient, is already known by the work of Alufian, Chen, and Marcoli. There's a non-accurate version of easy inductive formula for the Betti numbers of this space. So they use that. But our approach also can recover this formula. So you can prove the low concavity. So these means that if you fix a k, then the low concavity holds for every n except possibly except the finitely many n's. So that's why we conjectured this low concavities hold for O, N, and or K. And there is an equivalent version of this. So one is analog and one is indeed generalization. So we can consider the decomposition of these representations into irreducible representations. And then we can see the multiplicity, because, as we just saw the multiplicities of the trivial parts. And our question is, do they form a low concave sequence? There's another question. There's an equivalent version of the low concavity, or representation theoretic low concavity, which means if you tensor the k minus 1 piece and the k plus 1 piece, then it is the sub-representation of the square of the kth piece. And we check that this holds for n up to 25. This is a really big number. And also for the invariant part, we check that this is true for n up to 45. And okay, so the way we check these is coming from the recursive formula we established. Okay, there's a brief picture. I will just show the formulas. But the idea is like this. So this is a rooted tree. This is a root with a weight on the roots. And there can be attached some inputs here and also some other parts. So we can decompose these into the tree with one vertex and a inputs and other pieces. And then in our combinatorial formula, this piece is just induced representation of the tensor product of the UTIs here with some explicit representation. So using this, we can say that the recursion on this the set is controlled by the subset, which has a positive weight at the root. Yeah. The reason why we're considering only this set is these parts are allowed to have only positive roots, as I said in the defining conditions. Okay, so using these, we can write the formulas. The formula goes like this. So we consider generating series of these SN representations. So P is our goal, and Q is we put extra marking so that we can obtain some combinatorial formula using the blob sequence. And the Q plus correspond to the, okay, so this is a sum of UTs, and this is a sum of UTs, but it's only partial sum. We allow T only have a positive weight at the root. And here H is correspond to the trivial representation. We just put them to make the formula more beautiful or more concise. Okay, this is our formula. So firstly, this is the generating series version of the formula, the relation we write before. So for this, if you compute Q, then you can compute P. So this is how we write. And Q is the exponential of the Q plus. So if you can compute Q plus, then you can compute Q. And Q plus has its own recursive formula. So you can compute Q plus. And the combination of the last two is a equivalent generalization of the Urey-Manin's characterization of the generating series of the Poincare polynomial of M0n plus 1. I mean, this is a non-equative version of our result. Okay, so there's a more algorithm-friendly version. So you can see this, the Qn plus can be written down as some Qnj plus 1 with smaller nj's. So using this formula, we computed our representations. And there are also invariant version. So this is for the multiplicity version. So to compute the multiplicity of the invariant, the trivial representation, you don't have to compute the whole representation due to this formula. So that's how we compute these three polynomials up to 45. Okay, this is the end of my talk. Thank you very much.
Any quick questions? Yeah.
So you mentioned a new equivariant factorization of the Daejeon map from n plus 1 configuration to n configuration. Could you elaborate on that a little?
Are you talking about this?
No. In the first part of the talk, before log concavity, I guess, you mentioned the new factorization, new equivariant factorization, this one.
This
the
one.
bottom, right? Could you? Is
okay.
it possible to comment
yeah,
on that?
so I can briefly say that. So our result is so this is relative one-dimensional. So every fiber is one-dimensional, and so we factorize. Our factorization is a sequence of blowups, and at the end we have a P1 bundle. So and then we can apply the projective bundle formula and blow formula for each blowups. And more geometrically, every fiber is exactly the curve it represents. So if you pick a point here, then it is represented by a curve with n markings. And then the fiber is exactly that curve with n markings. There's n sections of these maps. And what the blowdowns do is you contract all the rational thetas until you have symmetrically until you have one or two components. That's our geometry. Yeah, thank you.
Okay. Any other quick questions? Yeah.
I couldn't hear the precise sentence, but I think he mentioned the FS of module. And yeah, but yeah, okay, I'm not an expert of that theory, but there's some theory of the so-called FS of module, and this is the case. This is some example of that. And I think the result of that, the consequence of that theory, as far as I know, is there's a polynomial bound for every partition. I mean, if you consider the sequence of partitions, so-called padded partition, and if you consider a multiplicity of that partition, then you can see how it grows when n increases. And it is not constant, but that theory tells us that it has a polynomial bound. So I think that's the only thing I know about that theory. And yeah. And but we can also say, we can also prove a similar thing. That we prove some different polynomial bounds for every irreducible the multiplicity of the irreducible representation. So yeah, I didn't write here, but it's in our paper, so I can explain it later. Thanks.
Okay, very good. So let's thank Donggun again.